Hey everyone, welcome to the channel. This is obviously Science Talk, your informal portal in all things science. Hopefully you enjoyed the first episode where we looked at the really exciting discovery of phosphine gas in the clouds of Venus. For today's episode, we're going back there and we're going to be looking at what exactly came out of the research paper. You'll notice in the background, I've actually posted the paper from Nature Astronomy. I'm also making the link available to you. What's really nice is that Nature Astronomy has actually opened up this paper for everyone. So you don't need to buy it, you don't need to do anything. All you have to do is go there, click on the link, and you can actually download the paper for yourself and have a read and see exactly what was happening in their research. So you might be thinking, what exactly is the purpose of an academic paper? Why is it so important? Why do researchers go through all this trouble to write a paper and then to have a paper available for other people to read? Why would they do that? Well, the reason is quite simple. It comes back to this whole principle within science called peer review. It's a way for us to actually scrutinize the science. Think about it in a different way. So, for instance, you might have a group of researchers, or perhaps a sole researcher working on a problem. This might take months, it might take years, it might even take decades to complete the research, or to have all the information available to come to some sort of hypothesis. The purpose of a research paper is to distill, or in other words, to actually summarize all the work that you've been doing throughout your research to put it into some form that other people can read. But more importantly, it allows for your peers, other researchers, other scientists, to scrutinize your work. What I mean by that is that it allows other researchers and scientists and perhaps even interested parties to look at your research and look at your methodology, in other words, your methods, and to see what exactly you've done. And there's two parts to this. It might just be informative to read a paper, and then maybe you might be able to formulate research of your own. Or alternatively, it might be a way for you to actually critique a paper, critique a work. And this is all part of the scientific method and part of the scientific peer review system. So how does this peer review system work in practice? Well, the idea is quite simple. So as I've mentioned, you might have a group or individuals working on this particular problem or particular research problem, I should rather say. Maybe a hypothesis is drawn. Maybe there's something really interesting that comes from the research. Well, you won't know unless you actually put all of that in some form that other researchers can read. Once the research is done, you write up a paper, and that paper is then submitted to a journal for publication. Now, this is an interesting part of the peer review system because what it allows for, it might allow other experts or perhaps people in a similar field to then go through an editorial process where your work is being vetted. Now, what could happen from this whole process of actually submitting a paper is, well, first of all, your paper might actually be rejected. And this happens quite a lot to young researchers. It even happens to older, more established researchers as well. And it's a way of actually finding issues, maybe finding problems with the research, or it might even be a way to actually to fix issues or structural issues within the paper itself. Once it goes through this process, or once it goes through the editorial process, either it goes right through and it becomes a published paper, or alternatively, the reviewers might actually provide some sort of feedback, and they might tell the editor, or they might tell whoever is responsible for the study that the work might need some fixing, or it might not be of a high quality, or it might not be suitable for the particular journal, etc., etc. And then they might even advise the authors of the paper to resubmit. In other words, go back, maybe rewrite it, or maybe rethink certain ideas, or maybe rethink methods, and then re-put it into some form that they can actually resubmit it for consideration. Now, many journals are different. And a journal like Nature Astronomy, for instance, or a journal like Science, have an incredibly impressive vetting process. So not all papers that are submitted to Nature will be published. In many cases, Nature publishes mostly the top tier of research. So the other purpose of an academic paper really is to inform or to become a springboard for other research. And that's really what's also important in terms of understanding why researchers would go out there and actually put a paper into some sort of journal. And this is exactly what happened with this research. So here we can actually notice, just from looking at the paper itself, we have a series of different authors. If you were lucky to have watched the Zoom talk that was given by the researchers, you would actually come to the conclusion, or you would actually appreciate the fact that a large team involved in getting this information to the public. And it happened over a couple of years. And that's something that's quite interesting. And that's something that you should also understand in terms of research, that it's not something that happens over a couple of days, it's not something that happens over a couple of weeks. In many cases, research can take years. And it might involve, in this case, when you have really important research or very exciting research or very controversial research, you might actually have a large team of individuals who are responsible for this. So here we have quite a number of different authors, and in many cases, these are people with different expertise and different levels of expertise. You might have an astronomer, you might have someone in physics, you might even have a geologist or whatever. So all these various different people contributed to this work. I definitely don't want to go through the paper point by point because, number one, I'm not a subject expert, and there's a lot in the paper that I don't understand myself. And that is fine when you read a research paper. In many cases, when you read a research paper, because it's new and it might involve new methods, so looking at it for the first time might be quite a daunting prospect. But I don't want you to be afraid of research papers. But if you are a lay person, I still want you to have a look at this paper. What I'm going to do for this video, though, is that I'm going to try to distill some of the more important parts that came out of it that you might find interesting. Now let's just frame the background again. In the first episode, I spoke a little bit about Venus, and I mentioned that the atmosphere is extremely dense. But what I didn't mention is the fact that the atmosphere of Venus is also extremely acidic. In other words, it's very corrosive. The other point to this as well is that the atmospheric pressure of Venus is very high. If you compare it to Earth, you're looking at an atmospheric pressure that is 100 times greater than Earth. And in actual fact, when we sent a probe to Venus, those probes generally don't survive very long because of the combination of pressure, the combination of density, and the combination of acidity. So if a probe goes to Venus, most likely it's going to be crushed and it's going to burn up. Now from this paper, Phosphine Gas in the Cloud Decks of Venus, they mention a couple of numbers. How much phosphine they've calculated, or how much phosphine their method has calculated for them. And it comes down to about 20 parts per billion of phosphine within the atmosphere. Now that's very small, but it is quite significant. The other thing that comes out from the research is that the abiotic processes that are involved in the creation of phosphine on this planet, or perhaps on the gas planets like Jupiter and Saturn, would not be enough to create this phosphine, especially not at the levels that they are reporting. Now, how did they do this? And this is really the part that I think people should understand, is that how did they come to this conclusion? So obviously the big question is, how did they detect the phosphine? They didn't send a probe, didn't go to Venus to sample, so how exactly did they do it? Well, the answer is quite interesting. They used two very different instruments on Earth to detect the very unique spectral signature of this compound using these two different instruments. The first instrument is the James Clerk Maxwell Telescope in Hawaii, and the other one is the Atacama Large Millimeter Submillimeter Array, also called ALMA sometimes. The key thing is, from the research that they've done, and particularly from the paper, is that the detection comes at two very different times. So the first one was happening at the James Clerk was in 2017, whereas the ALMA one happened in 2019. Now this is a very interesting point and something that you should think about if you're considering this phosphine idea. So remember, I already mentioned that the atmosphere of Venus is very acidic, and that makes it really interesting as well. So that also adds to the intrigue, because what we know about phosphine is that it can be easily destroyed. So if you have measurements from two different dates, 2 years apart, showing that there is actually phosphine in the atmosphere, then there must be a mechanism that is actually producing this phosphine over this period of time. Now remember, from the first video I did mention that in our solar system you do find phosphine being produced within the gas planets. I only mentioned Jupiter the last time, but it's also true for Saturn. Now, Venus is not a gas planet, And so those conditions do not exist on that planet. And it can't match the conditions that could pump out those sorts of volumes of phosphine. So what we do know is that phosphine can be produced abiotically, in other words, without life. And these could include even lightning strikes. So if you have lightning striking a phosphorus-bearing mineral deposit, you might actually produce some quantities of phosphine. And another possibility could even be micrometeorites. They can produce this atmospheric phosphine. From the paper, the researchers have ruled out these possibilities. So they believe that those sort of abiotic processes would not be able to yield this amount of 20 parts per billion of phosphine. So for the moment, all we have is the spectral signature. What we're not going to be seeing in any time soon, unfortunately, is a possibility of a lander going to Venus. And this is quite sad because it would have been really interesting if a lander could be deployed and put onto Venus, or even some sort of drone put into the clouds of Venus to sample what's happening. We can have definitive hard proof that the phosphine is within the clouds and that it's being produced within the clouds. So on Earth, we do find phosphine being produced in very low oxygen conditions. So for instance, within swamps or within wetlands, you might actually produce phosphine as organisms or plants or any sort of organic matter is slowly decaying or going through this process of decomposition. And funny enough, we also have phosphine being produced from our intestines. So if you do pass wind, you might be producing a little bit of phosphine as well. Interestingly enough, phosphine can also be produced by our volcanoes. What we do know about Venus is that it is tectonically active, much like its sister planet Earth, the planet that we're living on. It might even be that we've underestimated the amount of volcanoes or volcanic activity on the surface of Venus. So this could potentially be an avenue of phosphine production. Or in other words, I should rather say, an avenue of abiotic phosphine production. So in summary, this exciting research is still in its infancy. And what I mean by that is that it's going to take a lot more research and a lot more researchers to get on board and look at this question of phosphine being produced in the clouds of Venus. And what exactly is the method of that production? Is it abiotic? Is it biotic? Is it proof of life on Venus? I don't know. The fact that we don't know yet is what makes this so exciting. It's open for exploration, and that is really one of the key hallmarks of scientific inquiry. It's trying to find the answers to things that we just don't know. Discover new methods, using old methods, or adding to the data of what we already know. Anyways, that's it for me for the second episode of Science Talk. The next time I'll hopefully be looking at a different topic. So please subscribe, like, and if you want to, please leave a comment. I'd really like to find out what you think of the videos, and I'll see you next time. Bye.